morning, everyone. Myself, Ashu Sharma, Assistant Professor, Department of Computer Science and Engineering, ARIA Institute of Engineering Technology, and Investment. Today, we will see image enhancement in frequency domain. So, let's start with very first topic, Fourier series. Fourier series is basically any function that periodically repeats itself. It can be expressed as the sum of sines and cosines of different frequencies, each multiplied by a different coefficient. So it's a summation expression, you can say, between different frequency of sines and cosines, which is periodically repeats itself. So it's a continuous behavior that we can see from that Fourier series. It does not matter how complicated the function is, as long as it is periodic and meets some mild mathematical conditions. It can be represented by such a sum, which is sum along with that cosine and sine terms and that different coefficient with together. Now see that the Fourier transform basically are functions that are not periodic but whose area under the curve is finite. It can be expressed as the integral of sine or cosines multiplied by a weighting function. This sort of formulation is called Fourier transform. So when we say about the Fourier transform, uh, we can say it's again an integral of sines or cosines which are multiplied by a weighting functions, and this type of functions consider as Fourier transform. So important characteristic of Fourier series and transform. A function expressed as either a Fourier series or a Fourier transform can be reconstructed and recovered by an inverse process with no loss of information. So a function which is expressed as a Fourier series or as a Fourier transform, it can be recovered while applying inverse process without any loss of information. These characteristics allow us to work in Fourier domain and then return to original domain of the function without losing any information. So these tactics you may consider as lossless, that techniques that information is not going to be lost. Now, Fourier series or Fourier transform, there is a little question mark that Fourier transform, as we deal only with the functions of the images of the finite duration. So when we talk about the function, we talk about the images representation. So now we have introduction towards the Fourier transform and frequency domain. Now, one-dimensional Fourier transform and its inverse. Fourier transform f of u of a single variable continuous function fx, it can be represented by this expression f of u. Capital F of u is equals to that integration is taking place between minus infinite to infinite, and fx and e raised to power minus j2 pi ux dx, where j is 2 minus 1. So it's a complex that equality. You can say that we have e raised to power minus j2 pi ux, and j is behaving like an iota in a complex number, and its value is equals to root minus 1. So this is the expression that we use during that Fourier domain and Fourier transformation that apply for f of u. So now we can obtain fx, a small fx, by means of inverse of Fourier transform. So basically we take inverse of this expression. So f of x is equals to minus infinite to infinite f of u, and now it becomes e raised to power j2 pi ux, and that integration with respect to u, so it is du. So equation 1 and 2 comprise the Fourier transform pair. If we compare this expression, it is something that when we take the inverse of this, then we have this f of x equals to minus infinite to infinite fu and e raised to power, this minus becomes plus and j2 pi ux, and this is du. So this is that expression becomes, and these two equations that comprise consist of the Fourier transform pair. So this is the expression that we represent that. Now the Fourier transform f of u of a single variable, we may have that discrete function f x, small fx, here x range from 0, 1 to m minus 1. It can be defined as we take f of u equals to 1 upon m, and summation that x equals to 0 to m minus 1, we taking discrete function that is 0 to m minus 1. So we are taking that summation unit over here, and fx e raised to power minus j pi 2 ux upon m, where u is having value from 0 to m minus 1. Similarly, we can obtain original function using inverse DFT. So we simply put over here f of u. So f of x equals to 1. We have this summation u equals to that x equals to 0, and that range is given from x m minus 1, and f of u expression that becomes m that j 2 pi ux upon m. So x is lying between 0, 1 to m minus 1. So basically this unit is becoming this x is equals to u. So u equals to 0 to u equals to m minus 1. F of u expression e raised to power j 2 pi ux upon m. So this is the range that we have when we talk about the discrete functions from 0 to m minus 1. Now there are certain notes point that 1 upon m multiplier can be placed in front of that Fourier transform as 1 upon m, or inverse Fourier transform as 1 upon m, or when we take both Fourier transform and inverse Fourier transform, it will be 1 upon root m. That the location of multiplier it doesn't matter. A condition is that the product of multiplier in Fourier transform and inverse Fourier transform must be equals to 1 upon m. So that is 0 to m minus 1 that we have range with respect to u and x. Now there are certain points about the computation in 1D DFT, discrete Fourier transform. So to compute f of u, that start by substituting u equals to 0 in exponential term and find summation over all values of x, then substitute u equals to 1 in exponential term and repeat summation over all value of x. Repeat this process for m value to obtain complete Fourier transform. So we start with the substituting u equals to 0 in exponential term and find the summation over all values of x, and then substitute u equals to 1 in exponential term and then repeat summation over value of x. That repeat this process for m values to obtain complete Fourier transform. Now in this process there are n squared summations and multiplication to compute discrete Fourier transform, like f of x transform is a discrete quantity and has same number of components as f of x. Discrete Fourier transform and its inverse always exist. Now there is an overview that how this expression all about that frequency domain. We have a Euler formula e raised to power j theta. Sometimes we use I also for iota. It's equate equals to cos theta plus j sine theta, where cos minus theta from trigonometric property is cos theta. So the definition of 1D DFT is f of u equals to 1 upon m, and it ranges from that x equals to 0 to m minus 1, fx e raised to power minus j 2 pi ux upon m, where u ranges from 0 to m minus 1. And in the next expression, f of u equals to 1 upon m, summation x equals to 0 to m minus 1, f of x, then this cos 2 pi ux upon m minus j sine 2 pi ux, and that is wholes upon m. So this is the expression, and u is equals to 0, 1, 2, and so on up to m minus 1. So overview of frequency domain. Each term of that Fourier transform f of u for each value of u is composed of sum of all values of fx, and the values of fx are multiplied by sines and cosines of different frequencies. The domain, which is you can say values of u, over which the values of f of u range, is called frequency domain, because u determines the frequency of components of the transform. So this is from that expression that we have. Now each term we have according to this. You may see this expression. So it's a summation that we can say that cos theta and plus j sine theta along with that f of fx. This is that in the multiplication of that. So That's why this expression, you can say that summation takes place between the cosine terms and the sine terms along with the coefficients. Each of the n term of f of u is called the frequency components of the transform. So f of u is called the frequency component of the transform. And in general, components of frequency domains are complex quantities. As I said earlier, for convenience in the analysis of the complex number, often f of u is expressed in the polar coordinates. So thank you very much for being with us for this session. We have discussed about the frequency domain, Fourier transform, what sort of properties. We have discussed about the 1D the Fourier transform, how is it representing that thing about this as a summation of cosine and sine terms along with the coefficients. So in this session we covered little bit briefing about the frequency domain along with the frequency the Fourier transform in 1D frame. So thank you so much.